Okay, so now we are going to talk about the memory mapped IO. What is memory mapped IO and why do we need a memory mapped IO? So the normal processor uses its address bus to talk to RAM and ROM. Normal processor. In memory mapped IO, some of those same addresses are redirected to a point at hardware devices instead of memory chip. This we have already discussed memory mapped IO. That means if you consider our full address space, some of the address is for RAM and the other address is for our IO devices region. Okay, so here it is says that some of these addresses in our full address space is directed to the hardware devices instead of the memory, that is instead of the RAM. Like here, if you see our total address space for some RAM and ROM and for more RAM and ROM is there, but some of them is for our IO device region. So for temperature sensor also, for our motor controller also, some address if you see here are divided for our IO device region, some address, and here also these can be some for UART, some for GPIO, some for ADC, as you can see here. So you have to understand now that our complete address space, some addresses talking in memory mapped IO's case we are talking, some address, the complete address space is divided for RAM and ROM and also for IO device region also. So that means if I am saying that I am storing to this, means I am sending the data to the device at this location, right? If 2000, if it is LED, that means I am sending the data to device LED. Load from means I am receiving the data from this device because this address is matching to the IO device part, and it is, let's say it is of a sensor or maybe it is of a LED, it depends. So reading and writing the device is happening like store to and read from. The CPU doesn't need special IO. There is no special IO instruction. It is using the exact same load or store instructions. These are the instructions which is used for our memory. They will use this exact instructions that has been used for our memory, and the same instructions are used for getting data from the device or giving data to the device, right? So for doing that, we are using the same memory instruction itself. Now there is no special IO instructions. This is the case of what? Memory mapped IO. This is mainly happening in memory mapped IO. Fine. Now MCU, remember, microcontroller unit. This is actually a small computer which has all of these devices in itself, right? It is a one single chip and it is cheap and compact because everything, processor, peripheral device plus memory are all in this MCU chip. That is, it's compact, but it is also cheap. Okay, is on one single chip. Everything is on one single chip. That is our MCU chip. So memory mapped IO is how the processor inside the MCU talks to those built-in peripherals. Now using this memory mapped IO scheme is how the processor inside this, the MCU has its own processor, its own memory, its own peripheral devices, and it is chipped to it. How it can talk to the peripheral devices using the address, using memory mapped IO, the processor which is present inside the MCU can talk to those peripheral device. So when your code is reading a temperature sensor register, it's literally just loading from, that is from the temperature sensor registers address, it will load that. That is what the reading means. Okay, so MCU, that is a processor which is present in this MCU chip, is reading the data, or basically talking to, we can say, to the peripheral using the memory mapped IO. So the memory mapped IO is how the processor inside this MCU talks to those built-in peripheral devices. Now we have to talk about this SparkFun RedV board. Okay, RedV is a development board. Think of it like a playground where you write, test and debug embedded programs before putting them into the real product. Here, this is like, if you see, this is a big picture. Let's understand what is RedV board. So this RedV is a development board. As you see, it's like a development board. It's like a playground where you can basically write, test and debug all our embedded programs before we are putting it into our real product. Now, what are the features of this Red V board? Let's see. Now, there is a processor here in the Red V board. This is like a RISC-V processor, RV32 iMac. Okay, RV32 iMac RISC-V processor is the processor which is there. So, if you see here, the processor which is there is RISC-V RV32 iMac processor which is there in this Red V board. Okay, fine. So here this is RV32 means what? It is a 32-bit RISC-V processor, that is a 32-bit core it is. Now I means integer instruction, M means multiplication or division hardware, A is atomic operation, C is the compressed instructions. Now it is a 5-stage pipeline, means the CPU process 5 instructions simultaneously. It's a pipeline processor, that is, we know what is pipeline, right? 5-stage pipeline means 5 instruction can be happening simultaneously. So the processor in this Red V board, development board, it's like how we will write our data, test and debug these embedded programs here before we are putting it into the real. Before putting it into the real product, what we will do is that we can just test, run, write and debug our embedded programs in this Red V board itself. This Red V contains a processor, that is the, it's a 32 like we can say RV32 iMac it is called as. Now it is a RISC-V core processor, that is 32-bit core, and I means integer instruction, M means multiplication or addition hardware, then atomic operation is A and C is compressed instruction. Now it is a 5-stage pipeline processor. This is talking about the complete, you can see it's talking about the complete processor part here. Fine. Now the speed is 320 plus megahertz, that is it can execute over 320 million instruction cycles per second. That is what it means, that is speed. It is very fast for a small embedded chip, so it is very fast. 320 million instructions can be instruction cycles per second it can execute, that is the speed. Now form factor, if you see here, there is an Arduino UNO R3 footprint that is there. Now if here you see, you can see that the Arduino UNO R3 footprint. What is this? It is like, you know, as you see, it's the form factor, that is same physical shape and pin layout as the popular Arduino UNO, like the same thing, you know, Arduino means you can plug in an existing Arduino shield, add on board directly, lowers the cost, no need to redesign the hardware from scratch. So there is an Arduino UNO R3 footprint which can be directly placed here, plug in. So you can directly plug in any existing Arduino shield directly to here. We can directly add to our board, what Red V board, we can directly add this Arduino UNO R3 footprint. Fine. Now here if you see memory, see, instruction cache and data scratch pad. Now instruction cache basically stores the recently used program instruction for fast access. So you have to understand that there is this QC connector, this is called as QC connector, this is USB part, and this is the complete SparkFun Red V, that is what we are talking about, SparkFun Red V. Now here if you see, we talk about this Arduino UNO R3 footprint here. Then here you can see an instruction cache, 16 KB instruction cache and 16 KB data scratch pad. Now let's see what do we mean by this 16 KB instruction cache and 16 KB data scratch pad. Instruction cache means they store the recently used program instructions for fast access is stored in this instruction cache. Now data scratch pad is fast temporary storage for variables is this data that is fast. Temporarily we can store the variables here in this data scratch pad, and the instructions which are recently used is stored in this instruction cache. So scratch pad is faster than the regular RAM because it has no cache miss overhead. The CPU knows exactly where everything is, so it is something which is faster than the RAM, regular RAM, which the scratch pad, because there is no cache miss overhead in the data scratch pad. Because the CPU know exactly where everything is, that is why it is something which is considered to have been faster than the RAM, and there is no cache miss overhead. Now connectivity. Now how the connectivity? The connectivity is basically done using the USB-C and quick connector, right? Quick connector and the USB-C is the USB, which is used for programming and debugging. You are using USB-C. Quick connector, a plug and play 12C connector, lets you snap in sensors, that is Without soldering, how you can connect your sensors? It is a plug and play 12C connector is this Q connector. Now for programming and debugging, we have this USB-C. It routes through a NXP ARM Cortex M4 chip that act as a bridge between your computer and the RISC-V chip. Then you have Q connector, for it's a plug and play 12C connector which help us to snap our sensors without soldering. Sensors, how you can connect your sensors directly without soldering is how using this Q connector. Fine, using this Q connector you can basically do that. So there is Q connector and USB-C. USB-C is where programming and debugging can be happening. Okay, it actually routes through this NXP ARM Cortex M4 chip that would act as a bridge between your computer and the RISC-V, between this computer and our RISC-V chip which is there, a bridge between them. You have this ARM Cortex, right? You have this NXP ARM Cortex M4 chip. So this is used for programming and debugging, and this is to plug in our sensors, snap in our sensors without soldering. Okay, so that is the thing. Now here you can see it is USB-C is used for programming and debugging, and it is routing through an NXP ARM Cortex M4 chip, right? You can see there is an NXP ARM Cortex chip that is USB-C. Okay, so here this is a second hidden processor, what this NXP ARM Cortex M4 chip. So this is the red V board. Actually this is what the red V board is. Here if you see, there is one thing, that is this FE310 SoC Sci-Fi FE310 SoC. Now what do we mean by this? What it make? The designer is Sci-Fi, that is it is a pioneer of a commercial RISC-V. Okay, the type is system on chip, pipeline 5-stage, ISA is RISC-V. This is actually a ISA is 6.5. This is basically what the chip processor is actually, and peripherals are UART, SPI, 12C, all memory map, GPIO, or is this royalty free is a big deal. Companies don't pay licensing free to use this RISC-V like they would for ARM, making products cheaper to build. So here if you see, the FE310 SoC Sci-Fi is actually Sci-Fi, designer is Sci-Fi, and the type is what? System on chip. Type is system on chip. Here the type, designer is Sci-Fi, type is system on chip. Then we have the pipeline, 5-stage pipelining is the ISA is RISC-V, and peripherals UART, SPI, 12C, GPI, which is all memory mapped. So peripherals, ISA we know it is RISC-V, pipeline 5-stage pipeline, type is what? System on chip, and designer is Sci-Fi. This is a characteristic of this Sci-Fi FE310 SoC. Okay, that you have to understand. Fine, here so what happened is that you have a C code. Now first it will go to this RISC-V core, that is this main RISC-V core is this FE310 RISC-V core, that is our main core. It will load this address. So if I am saying that in temp I need to load this address, that is my C code. So my RISC-V core would issue this and load that to address this. So using memory mapped IO system, which is, we will see the address falls in an IO range, or if it is in the peripheral devices, then it will add that address to the load it to the temperature sensor, right? It will be the temperature sensor, physical sensor, and returns the digital value, that is your variable. That is the main thing that is basically happening here. That is, you have your C code, so that load from this address, this address reads, you will be first the RISC-V core, what it will do is that it issues a load to this address. Okay, the memory mapped IO system will see if the address falls in the IO range. If it falls in the IO range, then it will find that routes to that address peripheral. What is that address? In that address peripheral it will go, and it will read that physical sensor, and it will return the digital value, your variable. So it will basically issuing a load to the address, to this address. Who is issuing the load is done by the RISC-V core, that is our FE310 core. This is basically happening here. So you have to understand here in our this red 5 board, you have to understand, which is actually development board. What are the things that you have to understand here? This the processor is what? The processor is the Sci-Fi FE310. This is a core which is a RISC-V core, which is basically the processor is basically RV32 iMac RISC-V core is basically and the speed is 320 million instructions per cycle. Okay, then we have this instruction cache and data scratchpad, currently used instruction, and this is faster than RAM. It temporarily stores the variables during the execution type, faster than RAM because there is no cache miss there. The connectivity is this USB-C and Q connector. This is for programming and debugging. It actually routes through a second hidden processor, actually this USB-6, that is our ARM Cortex M4 chip, right? NXP ARM Cortex M4 chip. This would act as a bridge between our RISC-V chip and the computer, right? Between this there should be a connectivity, RISC-V chip and computer, that is done by this USB-C. Q connector is what? It is a plug and play. It is basically used to snap our sensors without soldering into our like our sensors has to be connected to our this RISC-V, that is done using this Q connector. This is like a play and plug 12C connector. USB is used to connect the computer with this RISC-V. Using it basically has this mini processor also, that is this NSP ARM Cortex M4 chip, right? Then we were talking about the features of our whole thing, that is this the Sci-Fi FE310 SoC, right? So to know that, we have said the designer is Sci-Fi. The type would be what? That is system on chip type. The pipeline ISA was the RISC-V ISA, peripherals UART, SPI, 12C, GPI, all are memory mapped. Then we said, first if you have a C code, let's say int temp is equal to, I am writing one address. So first what happened is that the RISC-V would, what it will, that is FE310 RISC-V core would load that address. Load issues a load to this address. Then using the memory mapped IO system, we will see whether it is belonging to the IO range. Then it will find that address peripheral. Now from that address it will read the physical sensor and the value, digital value it will read. That is what you are going to get as your variable, the value that you needed. Okay, thank you.